What's up? I'm Vin, and today I want to show how to use the chain rule in calculus. So we're going to go through these 10 questions. These are the two methods that we're going to use, and let's get started. Now for the first question here, we want to find the derivative of this y equals here. And for method 1, this is probably the safest method that you could use. It takes the longest, but it is very safe. So what we do first is you define u and make a substitution. And the u term here is going to be the inside term. So I let u equal 3x squared plus 7x. And then what we do is we make a substitution. So now what we have is y equals, instead of 3x squared plus 7x to the 10, this is just going to be u to the 10th power. So this simplifies things a bit. And what we want to do next is we're going to calculate dy du, and we're going to calculate du dx. So here, this is in terms of u and x. So this is going to tell us du dx. And du dx, if we just do the power rule straight across, is going to give us 6x, and then we have plus 7 for the derivative of 7x. And now that's calculating du dx, but we also need to calculate what is dy du. So we take the derivative with respect to u on both sides, and here we're going to use the power rule, and we'll have 10u to the 9th power. So then the last thing we do is apply the chain rule. Dy dx is equal to the product of dy du times du dx. So we have 10u to the 9th, that's dy du, and we're multiplying that with du dx, which is 6x plus 7, which we're going to put in parentheses because we're multiplying by a binomial. And then the last thing you need to do is your answer has to be all in terms of x. So we're going to make one more substitution at the end, and we're going to write everything in terms of x. So we have 10, we leave a space for the u term to the 9th power, and it's being multiplied by 6x plus 7. And u is equal to 3x squared plus 7x. So our final answer here to this question is this expression here. That's our derivative to the original y equals. Now, once you get a little bit better with the chain rule, you could kind of speed things up a bit, and you could use method 2, which is the shortcut. And the way method 2 works, first what I want to do is I'm going to rewrite this as 10x plus 1 to the 1/2 power. But the way this trick works, or the shortcut, is you start by taking the derivative of the outside function. So when I look at that expression that we're starting with here, I say the outside expression is a power of 1/2, and the inside expression is going to be 10x plus 1. So when I want to use this shortcut, when I say find the derivative of the outside, so this we're going to call dy dx equals, the derivative of the outside, we're using the power rule because the outside function is the power 1/2. So I'd have 1/2. The base we'll talk about in a second, but then I subtract 1 from the exponent. But it's the derivative of the outside. We keep the inside the same. The inside is 10x plus 1. So we're keeping that the same. Then the last thing we do is multiply or times the derivative of the inside. And if you look, the inside is 10x plus 1, and the derivative of 10x plus 1 is just 10. So now to simplify things a bit, we can multiply 1/2 times 10, which is 5. And now this is going to be equal to 5 times 10x plus 1 to the negative 1/2 power. If we want to rewrite our answer a little bit different here, we could write this in radical form. We'll have a 5 in the numerator with this constant, and then we could send 10x plus 1 to the negative 1/2 down as 10x plus 1 to the 1/2 power, or we could throw it back in a square root. So this is our final answer to the second question. So we'll practice with this shortcut once more. If I look at this expression, the first thing that jumps out at me is that the outside function, so just by glancing at this, the outside is the power -3, and the inside function, that's going to be the 7x to the 3rd plus 1. So when we go forward with this here, if we want to find the derivative, just know this piece here, the 5 is a constant attached by multiplication, so we just leave that alone. So now we use the shortcut. We're doing the derivative of the outside, and the outside, remember, is power -3. So we're going to bring that -3 down. We're going to multiply by the base, 7x to the 3rd plus 1, and our new exponent is going to be -4 because we're subtracting 1. Remember, the idea is we take the derivative of the outside and we keep the inside the same. That's why the inside is staying as 7x to the 3rd plus 1. So after we keep the inside the same, the last thing you do is times the derivative of the inside. The derivative of the inside, 7x to the 3rd plus 1, is 21x squared. So now if we clean this up a bit, we have -15 times 21, and that we just have to multiply the numbers together. So we have -15 times 21. That's going to give us -315. If I want to be sure, I could, of course, just multiply the numbers on the side like this. Let's just assume I'm doing all these without a calculator. And after we work this out, yeah, we're going to have 315, but it's going to be negative because we have a positive times a negative times a positive. So we have negative 315 x to the second. And now the 7x to the third plus 1 to the negative 4. What we could do with that is we could send it down as 7x to the third plus 1 to the positive fourth power. So here is our solution to the third question. Now, sometimes when you try to use the shortcut, you could be unsure. That's why if you go back to method 1 is very reliable. So what we do is we define u to be the inside function. So u in this case would be equal to 3x plus 1. And then we make the substitution for u. So we'd have y equals secant u. So then that's the first step. The second thing we would do is calculate dy du and du dx. So du dx, the derivative of 3x plus 1 with respect to x is just 3. And then here, dy du, the derivative of secant u with respect to u is going to be secant u times tangent u. So then when I want to find our derivative here, dy dx, or I could say y prime, we'll practice naming this many different ways. The derivative is equal to dy du times du dx. So the order that I multiply these doesn't matter. I could say du dx times dy du. So ultimately, I'm multiplying 3 times secant u tangent u. And remember, at the end, our final answer should be all in terms of x. So this is going to be 3 times secant u is equal to 3x plus 1. And tangent u, we're replacing that u term also with 3x plus 1. So here is our final answer to the fourth question. So now for the fifth question here, let's just say for this one we want to use the shortcut. So for the shortcut, we're going to do the derivative of the outside. So just by staring at this, one of the skills that you need is you have to be able to identify that the outside function is tangent and the inside function is going to be e to the x. Now, to take this derivative, we're doing the derivative of the outside. The derivative of tangent is secant squared. We keep the inside function the same, so we're keeping e to the x, but then we multiply all of this by the derivative of the inside, and the derivative of e to the x is e to the x. So our final answer, if we simplify this a little bit nicer, is going to be e to the x secant squared e to the x. Now, one thing I should mention, notice here I just wrote tangent, and on its own, tangent of nothing is meaningless, but this is just part of the thought process. When I say the outside function is tangent, I mean like tangent of, it could be tangent x, tangent of anything. But typically, we would never write tangent of blank. But it's something that you could think. It just helps you when you're doing the chain rule in your head. For question 6, I've seen questions like this throw students off because they have trouble sometimes identifying which function is on the inside or outside. That's why method 1 could be so reliable, because if we say, let's say u is equal to tangent x, and then we make the substitution, it's very obvious by looking at this that this is something that we will be able to differentiate using that first method, and it'll come out nice. Like, this just looks much cleaner than what we started with. So if we start taking the derivative of this, we have du dx. The derivative of tangent x is secant squared x. And dy du, the derivative of e to the u with respect to u is just e to the u. And then remember, dy dx is going to be the product of du dx and dy du. So now we just multiply those two things together, and we have this. But remember, our final answer at the end has to be all in terms of x. So then we have secant squared x times e to the u, and u, once again, is tangent x. So this would be our final answer to the sixth example. So for the seventh question, there's actually a really nice way to do this, but I'm just going to show you method 1 first. The safest way to do this, once again, is to let u equal 3x to the fifth, and then you make this substitution. You have y equals natural log of u. So then when you calculate du dx, this is going to be 15x to the fourth power, and then dy du is going to be 1 over u. That's our derivative of natural log u. And then remember, dy dx, we're using the chain rule now, is going to be equal to dy du times du dx. So I would have 15x to the fourth times 1 over u, which gives us this. And then when we make the substitution, to make everything in terms of x, u is equal to 3x to the fifth power. 15 divided by 3 is 5, and then x to the 4 cancels out completely and reduces the bottom power to a 1. So I would have 5 over x is our final answer. But the really cool way of doing this, you could actually do this without using the chain rule at all, is if you use properties of logs. Notice this is 3 times x to the fifth power inside. So I could split this up as natural log 3 plus natural log of x to the fifth. And then I could use one more log property and take this exponent on the inside and bring it out in front like this as a coefficient. So now when I take the derivative, notice this piece here, this piece is constant. So the derivative of a constant is 0, plus we have a constant times natural log x. So we have 5 times the derivative of natural log x is 1 over x. So this whole thing just simplifies to 5 over x. So just because we know the chain rule doesn't mean we have to use it in all scenarios. If you find a creative way of finding a derivative without the chain rule, that usually will make your life easier. So for question 8, we have an inside function raised to a power. For this one, I'll use the shortcut. So we'll do the derivative of the outside. So we'll do the power rule on the outside part, and that reduces the power to the power 4. And now we're going to keep the inside the same. So we have secant x plus tangent x. But now we're multiplying all of this by the derivative of the inside. And the derivative of secant x is secant x tangent x. Now we have plus the derivative of tangent is going to be secant squared x. So once again, we're doing the derivative of the outside. We keep the inside the same, but then we multiply all of that by the derivative of the inside, the secant x plus tangent x. But now this could be simplified a little bit nicer. Notice there's a common factor of secant x. So I could pair up 5 with the secant x. I still have the secant x plus tangent x to the 4th power piece here. But now notice this set of parentheses here. If I take out the secant x, I'm left with tangent x plus, and when we take out a secant x from secant squared, we're left with just secant x. But notice this term here matches this term being raised to the 4th power. Because of commutativity of addition, this is equal to secant plus tangent. So to simplify this a little bit more, we could say the derivative dy dx is equal to 5 secant x times, and we would have secant x plus tangent x going back to the 5th power, because remember, this is to the 1st power, so I just add the exponents, 4 plus 1, giving us an exponent of 5. So here's our solution to question 8. So for the next question here, let's say I want to use the second method. Let's say I want to use the first method, the U-substitution method. I would let the U term equal the inside, the secant x plus tangent x. And then that gives us y equals natural log of u. So when we find the derivative, du dx is equal to secant x tangent x, that's the derivative of secant, plus the derivative of tangent is secant squared x. And now dy du is equal to 1 over u. So now when we want to find the derivative dy dx, we're just going to multiply these two derivatives together, the du dx and the dy du. And notice this is going to give us a fraction. We have a u term in the denominator, and in the numerator we have secant x tangent x plus secant squared, which preemptively I'm going to factor out a secant, and we'll be left with tangent x plus secant x. Because notice what's going to happen here. We have secant x times tan x plus secant x. And in the denominator we have u, and u is equal to secant plus tangent. But I'll flip it. I'll write it as tangent x plus secant x. And you can see here we have matching factors that cancel. So our derivative dy dx is just equal to secant x. So that is our solution to question 9. Okay, for this last question, we'll go ahead and use the first method. So I'm going to let u this time equal the inside 4 cosine x. So then we have y is equal to sine of u. So then we're going to calculate du dx, which the derivative of 4 cosine x is going to be negative 4 sine x. And now here we're going to calculate dy du. The derivative of sine u with respect to u is cosine u. So then we have dy dx is the product of du dx and dy du. That gives us negative 4 sine x times cosine of u. But this, if we make the substitution, is negative 4 sine x cosine, and I'll put parentheses here because we're going to be plugging in a bigger term, u is equal to 4 cosine x. So here is our derivative, and this is our solution to the last question. Okay, well, this is going to conclude this video on the chain rule. If you found this video to be helpful, please like and subscribe. It really helps me grow the channel. And if you got any requests, just leave the topics you want me to cover in the comment section below. And thanks for watching.